Hello everyone, welcome to TypeScript Today. Today we're going to talk about ways we can manipulate type inference. Now you're already pretty familiar probably with one way to do this, namely the asConst assertion. When TypeScript infers the type for a variable based upon a literal we're assigning, it will try to infer a pretty wide type. So for example, here for the number we get number as a type, here for the string C we get string, here for the variable a we get an array, and here for the object we get an object type whose properties are similarly widened. So a is a number, b is a string, and so on. Now, if we actually want to preserve a more narrow type, we can use the asConst assertion. So we can say here asConst, and then n will be typed as the number literal type 1. We can do something similar for the string, and we get the string literal type. We can do something similar for the array, and then we actually get a tuple type, a read-only tuple instead of an array type. And for the object, if we do the same, then recursively all its literal types are preserved, all arrays become tuples, and all properties become read-only. But did you know there is a way to do something very similar using generic functions? Let's see what that looks like. So here we have a function foo. It declares some magic type parameters here, and then we can see here that the type it has inferred for the variable x, for the parameter x, is a type that's very similar to the type we're inferring with asConst. We can see that number literals have been preserved, string literals have been preserved, and tuples have also been preserved. So what is this magic and how does it work? Well, there are several pieces that actually make this work, and we're going to look at all of them individually. The first piece is how can we actually preserve number and string literals. So let's try a first approach. Let's declare a function with a type parameter n, and we say that we're accepting a parameter p that is an object type and has a value of that n type. Will TypeScript infer a number literal? Unfortunately not, n will be number in this case. The rule is that if you put a type constraint on a type parameter that is of a type that can produce literals, so for example if we say here extends number, then TypeScript will preserve the literal type. So now we have literal types for this particular variable. This of course works for other types as well. We can create a function that keeps string literals. Similarly, if we do extend string and we say here that we're passing in an object type with a value property that has the value foo, and we can see here that now t is also of type foo. So the literal type was preserved. If we were to take out the extend string, then we would again have string. We wouldn't have the string literal type foo. Now, this also works for more complicated scenarios. This also works if we don't only have one single type that produces literals, but we have a union of them. So for example, if we want to keep all possible literal types, then what we can do is we can define a union of all types that can produce literals, namely string, number, boolean, symbol, undefined, void, and null. So these are all types that can produce literal types. And then when we call this function, we can see here that v3 has been typed as string literals 1, foo, and null. All of them were preserved as we specified them in the parameters. Right? And all of this happens because this type constraint extends something that produces literal types. Again, without this, we would just get the very wide string, number, and null. Null, of course, is a type that can only have one value, so that still gets preserved. So this is the first part of it. We know how we can preserve literal types. The second part of it is how can we preserve tuple types? The answer to this, again comes in the form of a type constraint. So let's start out with something more simple. Let's try to create a function. Let's call it number tuple. And we say here that we're extending a number array. And we're taking in a parameter that is of this type t. Let's try to invoke this function. If we invoke it with an array literal, we see that the type has not been preserved. It still has a very wide type of number array. So how can we make it preserve our tuple? The answer is that we just need to add a tuple in the type constraint. So for example, if we add the empty tuple, and we say that t extends empty tuple or number, what will actually happen is that TypeScript is now in a mode where it will preserve tuple types. So even though our array literal is actually not assignable to this empty tuple, because it's not, it is assignable to the number array. Just because this constraint was present, it has changed the way TypeScript thinks about inferring t. Now, it wouldn't have worked if we just left the empty array here. Again, a random tuple is not assignable to the empty tuple, so we actually can't do this. But if we have both constraints, we have the empty tuple and a number array, then we get this tuple inference. I want to point out something that's quite interesting, sort of a quirk. It doesn't really matter if that is the empty tuple. Actually, any tuple will do. So for example, if we say here that we want to extend a string tuple of 1 or a number array, then TypeScript is still in this mode where it will preserve tuples, even though now we have a tuple that is it has a completely different item type to our array. So now we have a function that can take either an array of no matter how many elements, and it will preserve its tuple type, or we can pass in just a tuple with a single string. And a tuple with 2 strings will not work because array literal is not assignable either to the tuple with 1 element or to the number array. So it's not valid. So this is the second piece of it. This is how we can preserve tuple types. The third piece of creating the function we originally saw is to realize that sometimes it doesn't even matter if inference succeeds or fails for a particular type parameter. All that matters is that it's present. Its mere presence might change the way TypeScript thinks about inferring things. And we already kind of saw this back with the empty tuple. Another expression of this is, for example, in this function. We want to create a new function where we keep literal types inside an object. Now this is not going to work for nested objects because we say here that our object type only has values of type n, and type n will have to be something that extends this union. But it will preserve literal types for the first level. Let's see if it actually does that. We're calling it with this particular object literal, and we can see here that indeed properties have very narrow literal types. Now, has the inference for n succeeded? Did TypeScript infer a type for n? Well, if we look here, we can see that it actually hasn't. Narrowable is the type constraint. The type constraint is what TypeScript will use for a type parameter when inference has failed. Why has inference failed? Well, because n is actually not present inside the parameter list. TypeScript only infers type parameters from the parameter list, so from the argument list, rather. It hasn't managed to infer anything for n. It doesn't infer one type parameter based on another type parameter. However, just the fact that this type parameter was present has changed the way TypeScript will infer t. Because these values were assigned to something that might be a type parameter constrained by a type that produces literal types, then it has kept the very narrow literal types instead of widening them. I want to point out that if here we were to actually use narrowable instead of n, we see here that again TypeScript has widened the types and hasn't preserved literal types. Now the last piece here is to actually make this recursive. So for example, now if we try to add here an object type, we can see here that it won't work. It will fail because we don't support objects inside our T object. So how can we do this? Well, one way is we could add just another empty object here, which basically will allow us to put any kind of object in there. But what we see here is that the types for the nested object were not preserved. It widened them to number. It didn't preserve the literal types. But again, we can use our insight that just the presence of a type parameter can change the way inference works, even if inference fails for that particular type parameter. So let's add inside the possible values of t, let's add t itself. Now t will recursively be typed as this part, right? It will be typed again as something that can have any property, but its properties might have the value of type n. Now again, since this type parameter is now present basically at every level of our hierarchy, what we get is that TypeScript will preserve literal types because it sees that the value might be assigned to this n type parameter. So now we see that it actually preserves literal types even at nested levels, and this will now work for any level. We might also want to preserve tuples, and let's see how we can do that. So if we have here, let's call it t, and we have here 1, 2, let's see what happens. We can see that the literals were preserved because we have this n here, and it's again at every level now because we are typing this recursively through t. But we can see that tuples have not been preserved. Well, how can we preserve tuples? Well, again, we can add the constraint, the empty tuple, and that puts TypeScript in the mood to infer tuples whenever it sees an array literal. Now, we've managed to achieve the same result as the original function we saw, where we preserve literal types and we preserve tuple types where we encounter them. And now, since we have these building blocks, we can actually play around with them. We can do all sorts of things. For example, we can preserve both literal types and tuples like we already saw. But we could only preserve, for example, tuples if we wanted. Here we have a type constraint that actually doesn't include an n type. It only includes the empty tuple. So this means that literal types are narrowed. We get number and string, but tuples are actually preserved. And we can do the opposite. We can just preserve literal types if we don't include that the empty array. We see here that we have preserved literal types, but we have arrays. And we can also play a bit with what kind of literals we do keep. For example, we might want to infer Boolean instead of true or false, but we want to preserve all of the other literal types. Then we just say that n extends something that all the other narrowable types without Boolean, and then we can see here that t now has all literal types except Boolean. So we get a lot of flexibility from this, and we can play around with it however we want.